Let's talk about the Pythagorean identities. The trigonometric functions are related to each other through several important equations called trigonometric identities. We have already seen the reciprocal identities. Now we'll look at the Pythagorean identities. This is the most important identity, and you must remember it. So let's derive that identity. So let's look at a right triangle. And let's call this angle theta, and let's call this A, B, and C. Now, based off the Pythagorean theorem, we know that A squared plus B squared is equal to C squared, because this is a right triangle. Now, let's take that equation, and I'm going to divide each component by C squared. So if I do that, now I have A squared divided by C squared plus B squared divided by C squared is equal to 1. Now I can also change this by the property of exponents to the quantity A over C squared plus the quantity B over C squared is equal to 1. Now I can also replace the thing inside of the parentheses with trig functions. So if I'm looking at the angle theta, then A is going to be the adjacent side, B is going to be the opposite side, and C would be the hypotenuse. So A over C is going to be adjacent over hypotenuse, and I can write that as cosine of theta squared. And B over C I know is opposite over hypotenuse, which is sine of theta squared is equal to 1. Now, you will notice the notation when you're talking about exponents of trig functions. They will go here. So we have sine squared theta plus cosine squared theta is equal to 1. And that's just a convention. So, these two things here are the same thing. We just normally put the exponent in this location when we're talking about trig functions. So this is the main Pythagorean identity. It's very important. Please memorize it. And let's go ahead and use it to solve example 2, which says express cosine of theta in terms of sine of theta using the Pythagorean identity. So the way that we can do that is we can solve the Pythagorean identity for cosine by subtracting both sides by sine squared theta. And if I do that, I get cosine squared theta is equal to 1 minus sine squared theta. And then from here, I can take the square root of both sides. So the left-hand side ends up simplifying to cosine of theta, and then the right-hand side ends up simplifying to plus or minus the square root of 1 minus sine squared theta. And the plus or minus is there because it just depends on which quadrant the angle is in. So sine could potentially be, cosine of theta could potentially be the positive or the negative square root of 1 minus sine squared theta. Again, just depending on which quadrant theta is in. So here we have sine squared theta plus cosine squared theta is equal to 1, but it turns out that these other two are variations of the Pythagorean identities. So let's go ahead and derive those and see where they come from. So we're going to start with the original Pythagorean identity, which is sine squared theta plus cosine squared theta is equal to 1. Now, if I take this thing and I manipulate it a little bit, I should be able to get the second and third identity here. So this is the second and this is the third. And the way that I'm going to get the second one is I'm going to divide all of the terms in this equation by cosine squared theta. And that's okay. It will still be equal as long as I do it on both sides of the equation. Now, this thing here is equivalent based off the reciprocal identity to tangent squared theta. Actually, I'm kind of skipping a step. So I could rewrite this thing as sine of theta over cosine of theta, quantity squared like that. This thing here, the numerator and the denominator are the same, so that just simplifies to 1, and then I could rewrite this thing as 1 over cosine of theta quantity squared. Now, this thing inside the parentheses, based off the reciprocal identity, we know that that simplifies to tangent of theta. And I know that this thing here, based off one of the reciprocal identities, that is equivalent to secant of theta squared. And remember earlier I just said the convention for the notation is that we put it like this. So tangent squared theta plus 1 is equal to secant squared theta. And so this gives us the second Pythagorean identity. And we're going to basically do the same thing to get the third identity, except we're just going to divide by something different this time around. So in the previous example, I divided all of the terms by cosine squared theta. Now I'm going to divide everything by sine squared theta. And hopefully that gives us the third identity. Okay, so this thing would simplify to 1. This thing I can rewrite as cosine of theta over sine of theta, and that whole quantity squared. And then the last thing here I can write as 1 over sine of theta quantity squared, like that. I'm just going to draw a line to separate these two things. So that will give me 1 plus the thing inside the parentheses here we know is equivalent to cotangent of theta based off one of the reciprocal identities. And then this thing here, based off another reciprocal identity, is equal to cosecant of theta squared. And now I'm just going to rewrite it so that the exponent is next to the trig function portion. And there we have our third Pythagorean identity. So that is how you derive these. I generally don't even memorize the second and the third equation or the second and third identity because it's pretty quick to derive them from the first one. So I, in general, only memorize the first one, and then when I need it, I'll pull out the second and third one. But, that's completely up to you whether you decide to memorize the second and third one or just derive them from the first one.